Welcome back, ladies and gentlemen. We'll now transition to the technical session, and these presentations will be in a hybrid mode, accommodating both physical and virtual presentations. We have papers covering diverse topics: multi-agent systems for urban traffic, video-based product ordering, small object detection in satellite imagery, trends in open source software, and transfer learning framework on image. Presiding over this session is our session chair, Professor Shujoy Shaha. Dr. Shujoy Shaha is currently an associate professor and HOD of the Department of CAC, AI and ML of Heritage Institute of Technology, Kolkata, which he joined way back in 2005. He received his MSc and MTech degrees in computer science from University of Kolkata in 2003 and 2005 respectively. Later, he received his PhD also from University of Calcutta in 2021. His research interests include computational biology, natural language processing, agentic AI, brain-computer interface, etc. He has more than 20 publications in various international journals, conferences, and book chapters. Shujada, the stage is all yours.
Hello. Thank you, Aditya, for introduction. A very good morning to all of you. So welcome you all to the first technical session of the third day of ICAA 2026. Now, as per the schedule I have with me, there are 5 papers to be presented in this session. Out of these 5 papers, 3 will be presented online and 2 will be the physical presentation. So, should I start? Yeah, thank you. Who will be the first one? Second one? Okay, so the first paper to be presented, the paper ID 67, and that will be presented online. The paper title, Efficient Voice-Based Product Ordering via Lightweight Language Models with Low Rank Adaptation. The presenter is Jatin Goel from Vellore Institute of Technology. Hi. Hello. Can you hear me?
Hello. Yes, sir. Am I audible?
Yeah, you are audible. Are you ready with your
Uh,
presentation?
yeah, I'm sharing my screen. I hope my screen is also visible.
Visible. So you know that it will be a 12 minutes presentation followed by 3 minutes question answer, right?
Right, sir.
You may start.
Okay. So, good morning, respected session chairs and participants. I'm Jatin Goyal from the School of Computer Science and Engineering, VIT Vellore, presenting this work on behalf of all the authors. Today, I will be presenting our paper titled Efficient Voice-Based Product Ordering via Lightweight Language Models with Low-Rank Adaptations. This work focuses on building a practical, accurate, and deployable voice-based ordering system for e-commerce using lightweight language models. Over the last few years, voice-based interactions has become a natural part of how users interact with digital systems. In e-commerce, users increasingly expect to search for product, compare prices, and even place orders simply by speaking to a device. Voice assistants are now common on smartphones, smart speakers, and in-car systems. However, spoken language is very difficult from written text. Uh, People speak informally, use incomplete sentences, slangs, and different way of expressing the same intent. For example, a user might say, "Add 2 bottles of milk, get me milk, I need some milk." Traditional intent slot based pipeline struggle to scale across such diversity. At the same time, Large language models offers strong semantic understanding, but they are computationally expensive and difficult to deploy in real system or mobile environment. This motivates the need for an efficient, accurate, and deployable voice-based ordering system. Now, building such a system introduces several challenges. Firstly, we need accurate semantic parsing, converting free-form spoken language into precise structured data that backend systems can execute. Second, backend system requires strict output formatting. Even a small JSON formatting error can cause system failure. Third, full-time fine-tuning of large language models is expensive in terms of GPU memory, training time, and cost. Fourth, voice-based systems require real-time latency. Users expect responses within second or two. Finally, we must ensure on-device inference feasibility, especially for mobile phones and other low-resources hardware. Our work aims to address all these challenges in a unified frame. To solve these problems, we propose an end-to-end voice-based product ordering framework. At the core of our system is a lightweight language model, Gamma 3, with 1 billion parameters. This model offers a strong balance between performance and efficiency. We use low-rank adaptation or LoRa for parameter-efficient fine-tuning. Instead of training the entire model, we only train a very few percentage of parameters. The model is trained to directly generate structured JSON output from natural language commands. Finally, we apply post-training quantization to reduce model size and accelerate inference, enabling deployment on both cloud servers and mobile devices. This slide shows the full system architecture. The pipeline starts with the raw user speech, which is processed by automatic speech recognition models such as Whisper. The transcript model then goes through a text normalization stage where numbers, contractions, and formatting are standardized. This normalization is passed to LoRa-tuned Gamma 3 1B model, which performs semantic parsing and generates a structured JSON output. This JSON acts as a clean contract between the language understanding module and backend business logic. The backend can then perform inventory check, authenticate the user, and confirm the order. This modular design keeps the system clean, scalable, and easy to integrate into existing e-commerce platforms. We selected Gamma 3 1B as our base model because it offers strong language capabilities while remaining lightweight enough for efficient deployment. To specialize it for product ordering, we apply LoRa fine-tuning. With LoRa, the base model base remains frozen and only a small set of low-rank adapters matrices are trained. In our setup, only about 1 to 2% of total model parameters are updated. This drastically reduces GPU memory usage and training cost by preserving task-specific performance. For the training, we created a synthetic dataset of 20,000 voice-style ordering commands paired with their corresponding JSON output. The dataset covers different sentence structures, synonyms for common products, and quantities in both numbers and spoken forms. For examples, add 2 bottles of milk and 6 eggs to my cart is mapped to structured JSON representation with item names and quantities. A key aspect of our system is structured output generation. The model is explicitly trained to produce syntactically valid JSON, semantically correct content, schema compliant output. We use schema prompting, where the output format is embedded into the prompt so that model knows exactly which key and structure to follow. This allows the model to generate API-ready JSON outputs that can directly consumed by backend system. As a result, we eliminate the need of complex multi-stage NLU pipeline involving separate intent detection and slot filling models. We now move to experimental evaluation. The LoRa-tuned model was evaluated on a held-out test of unseen utterances. It achieves 94.6% exact JSON match accuracy, approximately 97% slot level F1 score. Exact JSON match measures whether the generated output exactly matches the ground truth. Slot level F1 measures fine-grained semantic correctness, whether the product names and quantities are extracted correctly even when formatting differs. These results shows that the model is both structurally reliable and semantically accurate. This graph shows exact JSON match accuracy across different methods. The zero-shot gamma model achieves only 45% accuracy, showing that task-specific adaptation is essential. A rule-based parser reaches about 75% but fails on linguistic diversity. A fully fine-tuned gamma model reaches 95.1% accuracy. A LoRa-tuned model achieves 94.6% accuracy, which is nearly identical to full fine-tuning model, while training only a small fraction of the parameters. This demonstrates the effectiveness of LoRa for structure semantic parsing. This slide shows the slot level F1 score. Both the LoRa model and fully fine-tuned model achieves about 97% F1. This indicates that LoRa model captures task-specific knowledge almost as effectively as fully fine-tuned. In practical, most end-to-end failures come from ASR errors or ambiguous user speech rather than parsing mistakes. We also evaluated deployment efficiency. On a server-grade GPU using FP16 precision, the model achieves around 200 tokens per second, a latency of approximately 0.25 seconds for a typical JSON output. For the mobile deployment, we apply 8-bit post-quantization using ZPTQ. This reduces the memory footprint significantly and enables on-device inference with a latency of 2.5 seconds on the modern smartphones. This shows that real-time on-device voice ordering is practically feasible. Now, this graph summarizes inference latency and memory uses across different deployment configuration. It highlights the trade-off between model precision, latency, and memory footprint. Importantly, even with quantization, accuracy degradation is minimal, making this a practical deployment strategy. The main contribution of our work are first, we demonstrate that lightweight LLMs can handle complex voice-based e-commerce tasks. Secondly, we validate LoRa as an effective method for structured JSON generation. Third, we provide empirical analysis of accuracy versus efficiency trade-off. Finally, we show real-world feasibility of deploying LLM-based voice agents on mobile devices. To conclude our work, our work shows that small, efficiently fine-tuned language model can deliver high accuracy while remaining deployable in real-time environment. In future work, we plan to extend the system to support multi-turn dialogue, improve robustness on ASR errors, and add personalization and multilingual support. Our framework lays a strong foundation for the next generation of intelligent voice interfaces in e-commerce. Thank you for your attention. I will be happy to take any questions.
Yeah, so thank you very much for your very good and timely presentation. So first of all, I go to the audience. Any question from the audience? Anyone wants to ask anything? Okay, so since there is no question from the audience, so I have one or two question. So can you hear me?
Yes, sir.
Okay, Jatin, you show the comparative study of your work with different models, right?
Right.
And you said that your model performs comparatively well with the other models. Now, my question is, have you done this experiment on the same data set on all these models that you have mentioned?
Yes, sir. I included the same dataset. Even I tried to generate some test dataset using some synthetic datasets and use the same models, the same set of models to evaluate the matrices. Hello.
Interested to know that one model I showed in your one of the slides that one model one model has the accuracy of 45% around, whereas your model is say 94-95% accuracy. So
I think this one slide. Hello.
any reason that you find out
Excuse me, sir. You are not audible for the
you
few
hear me?
seconds. Yeah, now I can hear you.
So I just repeat the question that this gamma 3 1B with zero shot model, it shows 45% match, whereas your model is it's saying that 94 or 95% around. So did you analyze your result that why it gives
Yes, sir. So, firstly, when I checked the zero shot gamma model, gamma 3 1B, without any quantization or without any fine tuning, it shows that 45% accuracy, which indicates that task specific adaptation is essential for the model. Now, when I check for the fully fine tuned model, when then I fine tune it a little bit by fine tuning the small parameters of the model by training it on our own synthetic data set. And I see that it achieves an accuracy of 94.6% accuracy. I also checked it with the fully tuned gamma model, which shows 95.1% accuracy. So I see that it is nearly identical to fully fine-tuned model while training only a small fraction of the parameters.
okay, okay. Okay, so so that's it. Thank you very much. Big round of applause for the author.
Thank you, sir.
Okay. Okay. So we move to the next paper to be presented. So it is paper ID 91, I think, right? Analyzing trends in community evolution in open source software collaboration networks. Uh, uh, three persons will be presented, and all three are the students of Computer Science and Engineering Department, Bharat Jawar, Harsh Lakhotia, and Arunima Shaha. Okay, so are you ready? All three of you? Now, although three of you will present, but you will get the same 12 minutes time. Okay, fine. Thank you.
Good morning to the session chair, the esteemed dignitaries, and the members of the audience. I am Arunima Shaha. This is Bharat Kumar Jhavar, and this is Harsh Lakhotia. And today we are going to present our research on the topic analyzing trends in community evolution in open source software collaboration networks. Before jumping into the main presentation, I would like to explain quickly why we did this research. So let me give you a simple analogy. Consider a group of 8 developers where everyone jumps onto every bug. No chaos, no structure, no specialization. Work overlap, bottleneck forms, and bugs take longer time to resolve. Now let's consider analyzing how the developers interact, who talks with whom, where the load accumulates, and examining emerging coordination patterns. Bottleneck shrinks and productivity improves. So now, if our analogy has meaning to it, that raises a simple but powerful question. Does evolution of the developer community influences bug resolution time? If it does, then bug resolution is not just a technical process, it is a social as well as a structural process, and understanding this structure is very important for project health. So the following is the agenda for today, and one by one we will explore them all. Here we can see bug resolution at the center, surrounded by 7 factors which directly or indirectly impact how quickly bugs will get resolved. Now, coming to the interesting part, on studying all these 7 factors in depth, we found something quite profound. On replacing bug resolution with community development among developers, we found that these 7 factors continue to play an equally important role. All these 7 factors have been identified through the synthesis of past research work. So, what is our contribution? Guess what? That is developer collaboration networks or DCNs to study community evolution over time. We will explain about DCNs in further slides. So, as I said, all the 7 factors have been identified from prior research, and here is the list. All the prior research work deals with specific aspects of the developer collaboration, like repeated interaction between the developers or the partnership diversity among the developers. But what they did not study is how the community structure evolves over time, and how this structural changes relates to bug resolution behavior. That is where our work is different. So by now, we all know what we are dealing with. So our research question is, does consistent trends emerge in the development of communities in large open source projects despite differences in context and scale? And to study this, we have framed our framed our hypothesis as community evolution influences key project outcomes such as bug resolution time. So now let's jump into some work, and I would invite my co-author Harsh Lakhotia to continue from here.
Okay, so now let's study the scope of our study. Now let's talk about the scope of our study. We have worked with 3 datasets: Eclipse, OpenStack, and Red Hat. All of them are of different domains and open source projects. Now let's talk about the methodology of how we have constructed the DCN. First, we have considered only the resolved bugs because unresolved bugs do not capture the complete developer collaboration. Next, we have considered bugs with 3 or more unique developers because we want to capture meaningful conversation that contribute to our DCNs. Next, we have mapped each of the bug to a temporal time period. And by the word temporal time period, I mean the entire dataset has been divided into 20 equal parts based on time, and each period is called a temporal period. For the terminology, the nodes represent the individual developers. The undirected edges represent the collaboration between developers who have co-commented on a particular bug. Next, we have the edge weights, which represent the unique distinct bugs that the developers have co-commented on. So let's have a look at a sample data that we have prepared. Here, bug 2 will not be taken into consideration like I just explained because it has less than 3 developers. So we are left with bug 1 and bug 3. This is what the DCN for them looks like. Here you can see D1 and D2 have an edge weight of 1. So they have co-commented on one bug, that is bug 1 here, and D1 and D3 have an edge weight of 2. They have co-commented on 2 bugs, that is D1 and D3. Similarly, D2 and D4 do not have an edge because they haven't worked together so far. Now that we had a look at the sample data, let's have a look how the actual data looks like. This is the DCN for period 1. This is the DCN for period 2. Now, here the graphs have been built cumulatively. That is, the DCN for period 2 has been built on top of DCN of period 1. This is the DCN for period 20. Now it has become a dense web of developers. Now we have constructed the DCNs. Let us have a look at the structural matrices that we will be working with. Here, I'll not be deep diving into the definitions of the terms, but rather what importance do they hold in our project. First, we have global clustering, which measures the local cohesiveness. Next, the density, which measures the overall network cohesiveness. Then we have four types of centralization. First, we have closeness centralization, which represents how effectively or how efficiently the developers communicate with each other. Degree, which represents how frequently the developers comment on a bug. Betweenness centralization, which represents how developers act as a bridge between two subgroups. And eigenvector, which represents how developers interact with already influential developers. Last, we have the assortativity, which measures how similar developers interact with each other. Now that we have prepared the DCN and we had a look at the structural matrices that we'll be working with, let's have a look at the results of the computations that we have done on the DCN. I would like to call Bharat on the stage.
Hello, 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 hello. Okay, so now let's dive into the results. As over here, you can see there are two graphs, one for global clustering coefficient, another for density. You can see a definite trend of decreasing. We are going to come back to this graph again back later in future. Let's see if we can have some other trends in other network matrices. As you can see, for Eclipse, OpenStack, and Red Hat, we don't see any definite trend in any of our matrices. Other than assortativity, it shows a slight increasing trend, but that's not significant enough. Another graph, which is visual representation for the cumulative average bug close time. Over here, you can see an increasing trend. Well, of course, it's cumulative, so it's going to be an increasing trend. But an important observation over here is that there is no drastic change in any of the period. From another period to another period, there is only a small change that indicates it's either decreasing the bug resolution time or it is remaining the constant. Coming back to our important global clustering coefficient and density network metrics, we can see we will take global clustering as our primary indicator to indicate uh, the bug resolution time. Global clustering, what does it mean? In layman term, if A is connected to B and B and C are connected to each other, it forms a local triadic closure. Well, now that we have our independent variable in global clustering, we all know that a single matrix can't give reasons to find bug resolution time. Similarly, as weight gain depends not only on food intake but exercise and metabolism, upon doing some correlation analysis, we found out that closeness centralization, eigenvector centralization, and authority are somewhat related and within the real limits when compared with global clustering, our primary focus. Now, coming to the results, we see all models for Eclipse, OpenStack, and Red Hat are giving a strong explanatory power with R square value exceeding from 0.94. Interesting results over here are that the Eclipse is giving a negative inverse relation of minus 785 and Red Hat gives a positive, that is a direct relation of 357. And whereas OpenStack is giving a positive result but not that significant enough. What does these results signifies? Over here, we are going to accept the alternate hypothesis. Sorry, we are going to accept the null hypothesis and reject the alternate one. As we can see that global clustering coefficient consistently shows a measurable relationship with the bug resolution time. This indicates our primary focus on community structure, which is that yes, there is a factor in global clustering coefficient which gives an impact on the complete time of bug resolution. What does our research implies? Our research implies that it is not just a technical process but a social one. We have a counterintuitive idea that less collaboration gives us better bug resolution time, whereas now if we go to threats to validity, we have checked for construct validity, internal validity, external validity, and our sources of the data sets are reliable and reproducible. I would like to conclude by saying that our goal to check if community structure does have an impact on bug resolution time, well, yes, it does have. The parameter which consistently uh, shows a better factor is global clustering coefficient, although the direction of the impact depends heavily on ecosystems and project. Thank you. Thank you, speaker. If you have any questions.
Thank you very much, all three of you, for the nice presentation, and more importantly, the timely. You finish it on time. Thank you very much for that. So let's go back to the audience. If any question from the audience, if anyone wants to ask. Okay, someone wants to ask the question.
In one of your slides, you showed that the eigenvectors represent the closeness versus there was some metric. Uh, as far as I know, the eigenvectors represent the direction of maximum variance in the data. So why are you choosing the eigenvector for that, and why is that the maximum variance for in this case?
Well, you know that we had various matrices, right? We had assortativity, we had four types of centralization, we had global clustering as well as density. So we did correlation analysis by having heat map, and we checked with the primary focus keeping the global clustering. We checked if any other matrices can be our covariates, and by giving us the heat map, the only three factors which were under reasonable limits for in the heat map were these three, and we needed some covariates to help us build a multiple linear regression model, and thereby we chose these three factors.
Any question? Any more question from the audience? Okay. So now I have some questions for you. First of all, very interesting work that you have done. You please kindly go to the result section. Okay, first of all, can you tell me what this period stands for? What it represents?
Sir, the entire data set, the entire time period of the data set has been divided into 20 parts based on time. So period one represents, so let's say we have a data set ranging over 20 years. So the first period will be 1 year. That is what period means here.
Okay, fine. Achha, second one is where from did you take the data?
Sir, it was available on web.
It's publicly available data.
Web scraping.
Okay, fine. And the third one is you go to the result section where you compared the result. Yeah. Now all the parameters that you have taken, right? And you have done that experiment. Now I'm sure that there are many state-of-the-art works exist on this topic.
Yes.
Have you done any comparison with all these existing works?
Sir, not that we know of, but uh,
So our work deals with the community structure of it, right? We are not dealing with any other factors other than community structure. We are dealing with factors that the network are going to build. Our main idea was to build a developer collaboration network and check if any structural patterns can be seen. Our work will help us, our work will help project managers to build a structure and particular structure. And also I would like to mention, as you can see over here, we have a decreasing trend in global clustering, right? And what does global clustering mean? It means that for if forming a collaboration, if there are collaborations between the developers, and you can see across the periods the collaboration is decreasing, this will help project managers know that with time, since the collaboration has been decreased, but in this graph we can see that the bug resolution time hasn't been increased with period. That means less collaboration can get us better productivity. This is what we are going to help.
No, that I understand. But my point is that if you don't compare with your result with the other existing results, then how can you say that your work is better, or how can you justify?
Definitely. We are not
Yeah.
saying our work is better or better than anyone. We have done this work. I don't think I haven't seen, we have seen many other research, and many of our esteemed guests over here have done research on this. And not that I know of anyone has done particularly for these factors.
Okay.
This is the first, I guess, or maybe not. I don't know for sure.
Fine. So that you may.
Definitely.
Yeah, as a
we
future.
can have our
future
future work for that.
Okay. Okay. Thank you very much. A big
Sir.
round of applause for.
SM
all
sir
three
has
of you.
the question. SM sir
Oh.
had the question.
Yeah. Please.
What do you mean by the word cumulative? Means once you add the period, you take some more bugs and then calculate the average? Is that?
So we don't take more bugs. Like for period, we have just like he said, we had just for example, we have 20 years of data and we have divided into periods. For period one, for complete for 20 years, let's say we have 10,000 bugs. For period one, there was let's say 2,000 bugs. For period two, let's say there were 3,000 bugs. So on computing DCN for period one, there was a network for those 2,000 bugs. And for period 2, we constructed for 3,000 bucks, and cumulatively on the network of 2,000, we built upon the network of 3,000. That is the
So the network is cumulative.
Yeah, the network is cumulative, as well as the results are based, so that we can get a trend.
But you said the bug closure time didn't increase, but at least for one green line, I saw that it increased, right? So for Eclipse.
Yeah, for Eclipse, it is increasing, but not drastic. Like for Red Hat and OpenStack, though, we can see that it's not increasing. But if you see,
It's hardly increasing, yes.
it's slightly
So
increasing.
any explanation for that?
So
why for these two it didn't increase, but Eclipse is showing a different pattern?
Sir, the only explanation for that is that all the three data sets are for different projects, and projects vary from ecosystem.
I think Eclipse has a size smaller than the other two. Is that?
We can have the size over here. Wait. Over here, you can see that for Eclipse, there were around 13,000 unique bugs. For OpenStack, we had 25,000.
It's a similar size.
Way more than Eclipse.
Okay.
Thank you very much. Any question? Okay. So big round of applause for all three of you. Thank you. Thank you very much.
Thank you, everyone.
Okay. So we move to the next paper presentation, paper ID 93, with title a transfer learning framework on image transformed sensor data for smartphone based human activity recognition. Presenter Anindita Shaha from Technomain Salt Lake.
And my, yeah, and it's okay. It is okay. I think it is okay. I think it is okay.
A presentation to the presentation. Okay.
Good morning, everyone. My name is Anindita Saha, and I am working as an assistant professor in Technomain Salt Lake. This paper is a work of my student. As you can see, Shubham Dash is my student, and I'm a proud teacher of him because this is his first endeavor. And Dr. Chandray Chaudhary happens to be my guide in Jadavpur University, from where I'm currently pursuing my PhD. To begin with, I would like to say that this is a work on transfer learning. Transfer learning is the basic essence of this work. I would just like to tell you a little idea about it. Transfer learnings are deep learning models. In fact, what shall I say? It is a exaggeration of the deep learning models where we need very little. The existing models are trained on huge data sets, and for training to them to the target models, we do not require that much of data set, and that is the essence, that is the advantage of using a transfer learning model. In a nutshell, what we have done in this work, the first challenge was collecting a huge data set, which my students have done, along with Shubham also. And in that data set, we had 5 activities: standing, walking, sitting, laying, and jogging. So 2 of them happen to be dynamic activities and 3 of them are static activities. So our main work was to show that how deep learning models affect the accuracy of recognizing activities. So what we did after collecting the data, it was a huge data set containing around 15 lakh rows. And after that, what we did, they are all collected from smartphones. And we have used 5 smartphones here from different, for different users. So 5 different users were there. They have used 5 different smartphones and they have collected data on these activities. And after that, we have merged them and we have applied deep learning models on raw data sensor, which is 1D CNN. And then we have converted the raw data into images. And then we have applied 2D, two-dimensional CNN. And then we have applied transfer learning. We have used 2 models of transfer learning. One is ResNet 50 and the other is VGG 16. They are traditional ones. And we have shown how the accuracy and other performance matrices differ. So this is the nutshell of the work. And to introduce, I would just like to give you a brief idea about human activity recognition. This has been a quite important topic in the last 10 years we have seen. And this is very useful for identifying different activities of human beings, and especially taken from smartphones, because we know our smartphones are embedded with lots of sensors and it can be data can be taken from there. So we have used a particular application called G Sensor Logger, which is readily available in Play Store, and you can download it and you can capture the activities from there. So that's what my students have done. They have captured through smartphones via that app, and they have taken the data. So collection of the data set was the first job that we did. Next, we have talked about the motivation, because we found that deep learning have been widely used. But the only challenge that we have in deep learning is that it requires a huge amount of data set, which is sometimes very difficult to get. We tried to collect, but still we were going a little further back. So hence we tried to apply transfer learning, which is already pre-trained models like ResNet 50 and VGG 16. And we have seen how a normal deep learning model like 2D and a pre-trained model like ResNet 50 and VGG 16 are having effect on the collected data set by us. So this is a little framework. What we have done, as I said, again in a brief, we have collected the time series data from smartphone through that G sensor logger. And we have applied a 1D CNN, which is plain DL, deep learning, on the time series data. And then we have seen that the accuracy gives us, the accuracy is given to us as 89.00. And then what we have done, we have taken that time series data and we have converted into images. And then we have applied 2D CNN, because as we know, 2D CNNs are, as the name suggests, is 2D. So we need images for that. So raw signals cannot be used for 2D. And then we have applied our deep learning model on that transformed data set, and we have got an accuracy of 96.29%, which is definitely a sharp increase. But then again, we wanted to see that in case we do not have the advantage of huge data set, then how can transfer learning help? So in that case, we took the same amount of images and we applied these transfer learning models, TL, on the transformed data set. And we have seen that VGGNet gives us, and one more thing we have done, which is a novelty of our paper, which is we have tried 3 input resolutions. That means we have tried to convert the images into 224 into 224 size image resolution, which is a standard for deep learning. We have also reduced it into 180 into 180, and again increased to 300 cross 300. So basically the experiment is done on 3 types of image resolutions, just to show that how the TL models differ when the image size differs. And in that case, what we have seen, this is precisely the data set. Device type is smartphone, and the data set collected is by users in real time. They have taken the smartphone, they have walked, they have gone up, and they have sat, and they were standing, and they did all the activities I mentioned. And we have number of, definitely the features are 4, because we have the x-axis, y-axis, and z-axis, and the activity name, which we have labeled later on. So this is how the image look like. We haven't used any standard ones because we have kept it for the next paper. And we have just used the normal images, which we can understand from there. And see, this is how the static and the dynamic activities look like. From the picture, we can understand. And then we see the difference of work in 1D and 2D. In 1D, this is the graph that we have received. And in 2D, that is the graph that we have received and put in the results. Then we go to the transfer learning results, where we see that transfer learning, in case of ResNet, it has given me the best accuracy at the resolution of 180 cross 180. Whereas when we wanted to go for VGGNet, we saw that it is giving us the best resolution, the best accuracy in the image resolution of 300 cross 300. So from here, we can understand that how the transfer learning models, even if they're trained from the same data set of ImageNet, basic data set, still they are differing in when the image is getting changed, image resolution is getting changed. So one thing that we have concluded from here is that we have to be very careful about the image resolution when we are choosing the particular transfer learning model. And this is the graphical representation. As you can see, as I said, that for 180 into 180, that is how VGGNet performs. And the best resolutions are evident from the slide. This is the comparative model of, comparative results of all the models, where we have also shown the other performance matrices like precision, recall, and F1 score. And majorly, we are concentrating upon the accuracy part, where we can see that ResNet 50 works best, gives us the best result of 96.60 at a resolution of 180 cross 180, whereas VGGNet, when we go for the higher resolution, it delivers us the better results. One of the reasons might be the structural difference, because residual networks, which is ResNet 50, is basically on those, they don't have a proper deep learning structure, whereas in VGGNet, we have 3 cross 3 convolutions. Anybody who is aware of the fact will be able to figure out why it is. Okay, so that's it. I think I've been able to finish. Thank you so much for listening to me.
Okay, thank you very much for your presentation. So now move to the audience. Any question? Anyone wants to ask any question to the speaker? Okay, so if there is no question from the audience, so I want to ask 1 or 2 questions. First of all, what is the size of the data set that you have taken?
Yes, the size of the data set was, sir, I would like to tell you in details. My students took every activity, what we have done, we have, we have defined a particular minute for them, say for 6 minutes of walking. So for 6 minutes of walking, I found that we have got 60,000 rows for that particular CSV. And then for 5 such people, we have 16 to 5, which is 3 lakhs. So
So 5 such means for 5 different users.
yes, 5 different users with 5 different smartphones.
And you have collected your own data.
Yes.
Okay.
The first thing is the first challenge was to collect the data, because data set, we could have done the work in Wisdom or Opportunity or UCIR, which are benchmark data sets, but I prefer to do it in a collected data set just to see how it works when the user itself wishes to collect and apply our models on that.
Okay, but the point is,
So I would just like to finish my answer, sir. So entire data set was 15 lakhs of rows, because 5 users, 3 lakhs each. So the total data set was 15 lakhs. The rows, number of rows we had, 15 lakhs into 4.
okay, now I'm sure that there are many state-of-the-art works is going on this domain, right?
Yes, sir.
And you have used the transfer learning based model. Okay, but in your result that you have shown, I did not find any comparative study with the other models. Have you done anything regarding this?
Sir, in my paper, there is a section which is related work where we studied many papers, but we could not find anyone. I mean, like some of the papers were working on standard data sets. Some of the papers were working on collected data set, but the models were different. So we found that there is no such work which is comparing from basic data, deep learning, like 1D, then transforming the raw data to image, and then going to 2D, and then going to the transfer learning. So this particular pipeline was not maintained by anybody, as far as I know, as far as my research knowledge goes. So this is what we have studied so many papers, and we found that there is no pipeline through which we can figure out that how normal deep learning can be converted to, or can be taken up to the transfer learning level.
Okay, so maybe you can think about this as your future work.
Yes, one of the journal is being planned.
Okay. Thank you very much. A big round of applause for the speaker once
Thank
again.
you so much for listening.
Thank you very much. So we move to the next paper.
For the next 2 online presentations that were there, which we could not do it on schedule because the speaker connected with us, but we're still having some technical issues. We cannot connect with Likhit.
So let's
We'll
play
do
the
a
video.
Yeah, we'll do a recording for
Yeah.
both.
So which one we start with?
Likhit. We're doing the first one.
59. Paper ID 59. Okay. So so since the author is not available to present its paper, so we play the video, recorded video. Paper ID 59 with intelligent multi-agent system for urban traffic signal control, leveraging reinforcement learning and graph neural networks.
route directly connecting
This means all the traffic lights share the same branch. Even though they share the same branch, the graph attention network ensures that each traffic light only pays attention to its own neighbor. The most important part here is the centralized critic, which you see on the right. During training, this critic acts like a teacher. They see everything happening in the city and tell the traffic light if they are doing a good job as a team. Once the training is finished, we remove the teacher. The traffic lights can then work on their own, using what they have learned. So you might ask, how does a traffic light know which neighbor is important? To answer this, we use something called the attention mechanism. Imagine a traffic light asks a question. Do I have space for more cars? Its neighbor answers, I am sending a lot of cars to you. The model compares the question and answer to calculate an attention score. If a neighbor is sending a lot of traffic, the score is high. This tells the traffic light, pay attention to this route. A lot of cars are coming. By doing this, the agent can predict traffic before it arrives and prepare for it. To teach our agent, we choose an algorithm called short order critic. We choose this for three reasons. First, it encourages the agent to explore. We do not want them to get stuck doing the same thing forever, like always keeping the main ground green. Second, it handles random change very well, which is important because traffic is always changing. And third, it learns very fast because it can remember and reuse past experience. We also design a special reward function to guide them. We want to reduce the queue length so the car moves faster. We also punish the lines if they switch color too often to keep traffic smooth. Most importantly, we put a high priority on bus waiting time. We want the system to have the public transport move faster than private cars. This slide summarizes how we train the AI. We use a strategy called centralized training with decentralized execution. We take data from the memory buffer, then the centralized critic, the teacher, use global information to judge the action. It updates the network to make them better. Think of it like a football team practicing. During practice, the coach stops the game and tells everyone where to move to win. That is the training part. But during the real match, the coach stays on the sidelines and the players must make decisions on their own. That is the execution part. To test our system, we did not use a simple fake map. We used a real map of Bosnia area in Bologna, Italy. As you can see in figure 4.1, we ran a simulation on a software called Sumo. This scenario is quite difficult. It had 8 intersections with traffic lights. The traffic is mixed means we have both regular car and big bus. The bus has their own routes and stop. This makes the simulation very close to real life. So how do we know if our system is good? We compare it against the standard fixed time control. Since the most cities today still use fixed timer, this is the best comparison to make. We measure 14 a vendor's travel time to show how long it takes to finish a trip. A vendor waiting time, how long cars sit at red lights. Time lost, how much time is wasted compared to an empty road. And total hitting vehicle, how many time car have to stop completely. Our goal is to make all the numbers as low as possible. Now let's look at the results. I think the numbers speak for themselves. Please look at the table. Our system works much better than the fixed time control. We reduce the average travel time by 89.3%. It went down from over 660 seconds to just 33 seconds. Even more impressive is the waiting time. We reduced it by 98.2%. This means cars must never had to wait at red lights. Also, the number of cars that had to stop dropped by over 84%. This shows that the traffic light learn to work together, creating green wheel, so car could drive through smoothly. To finish, I would like to summarize what we have done. We built a new system called Graph Attention Network in a multi-agent reinforcement learning system. This system allows traffic lights to work together by sending their neighbor. It learns in a stable way and performs much better than the old fixed time system. However, there is still work to do. In the future, test this on much larger map and maybe a whole city. We also want to find ways to move this system from computer simulation to real hardware on the streets. Thank you. That brings me to the end of presentation. We believe that using AI like this is the key to solving traffic problem in our growing city. Thank you very much for listening. Hello everyone. Thank you for coming to our presentation today. My name is
since it is a video presentation, so there is no point for question and answer. So, a big round of applause for this presentation from the author's point of view. So, fine. Thank you. So, we move to the next paper. No? Video আছে তো? Yeah. He's present online.
We've managed to connect with him, so we'll take his presentation.
Fine. So the last paper in this session, paper ID 79, the title is Leveraging Small Object Detection in Satellite Imagery Using Dual Attention Augmented Single Stage CNN Model. And the presenter, I think, Likhit Yamanaru from Amrita Vishwavidyapith.
Hello, can you hear me? Hello? Hello, am I audible?
Hello. You hear me?
Yes, yes. So I am presenting the paper. So shall I just share the screen?
Your screen.
So I'll begin.
May start.
Okay, fine. So good morning. I'm going to be presenting the paper about the small object detection in satellite imagery. And this paper is not just focused on small object detection, but also on the medium-sized objects within the satellite imagery. And that is one key point within our paper. We have used to summarize the entire work, we have basically used we have modified a YOLO model, YOLO 11 model with the global attention module and ECA attention modules. So I'll begin. These are what all I'll discuss about today. The introduction I'll start with. So as you can see here, I have two images. One is of what looks like the sea, and the other side you have this airport. So what I do here is that I want the model to identify where all are these, which all are the planes, which all are the ships, and there's also we are going. This is used in like to identify vehicles on road. In this, I have just used the ship and the airplane, but the data set also contains identification of vehicles on road. And here you can see that these planes are quite large. They can easily be identified as planes in the image. But if you look at the ship, there are actually two ships, and you can barely just see one. This is a very big challenge in the small object detection because even as a person, we can barely identify that there is another
What
ship over here
happens?
in this image.
You are
Uh,
not. You are not audible.
oh, is it? Oh, just 1 minute. Hello? Hi. Hello? Am I audible now?
Can you hear me?
I can hear you, but am I audible?
Continue.
Okay, I'll continue.
Sure.
Okay, okay. Can I just ask, like, where did I get cut off?
Introduction slide.
Okay, right here itself, right? Okay, I'll just summarize from beginning. So basically, I was telling that there are two images. One is like an airport, and the other one is the sea. In the airport, you can clearly see that there are aeroplanes all around. And as a human observer, you can easily identify which are the airplanes. But if you look at the sea, you can barely identify the ship. And although you can see that there's only one ship, there are actually two ships in this image. And that makes this small object detection particularly challenging. So our approach was that if we can identify that this is the sea, we can let the model to know that it should particularly search for the smaller objects within the sea, right? That way it can possibly identify the smaller ships within the sea. And that was our whole idea behind adding the global attention module. And following, I will explain the other reasons for adding the ECA module as well. So in the literature survey is where we got the idea of adding this global attention module. So there was one paper where they were identifying the drones within the sky, and these were pretty small. However, these were like only focused on small object detection and not suppose they were considerably large, the model started losing accuracy. That was the downside to this. It was done on YOLO V8, and we have used YOLO V11 in our model along with other attention modules, and this is what we bring in new to this field. About the data set, we have use the Sky Fusion data set, which is available in Kaggle. Due to the class imbalance, we had to do some data augmentation like blurring, rotation, flip, and such augmentation techniques to get the ships higher. Initially, the images of the ship were much lower. And in this way, we have trained the model and validated it. I hope the words are clear, but if it's not, I'll just go through them. So we start with getting the Sky Fusion dataset, then we do the pre-processing. And following the data augmentation, we have first tested it on the base models of YOLO, which is YOLO 8, YOLO 9, YOLO 10, YOLO 11, and YOLO 12. These being the most recent base models at the time. Following this, we did this to identify which base model should we modify to get the best results in the next stage. And in the next stage, we have modified it with the attention modules, which is being GAM and ECA. And we have also done just pure YOLO and one of them. I'll go through them in the further stages. And following this, we have evaluated the model and concluded that the hybrid of the GAM and ECA is the best one. So I'll talk about the GAM attention module. So it's heavy, like as you see here, I have explained before also, we wanted the idea that the model will see the sea around it, or just identify that this is a place where ships can be found. So it will focus more on the ships. And this was the whole idea about adding the GAM attention module. But the core issue of this was that it required a lot of training because of the additional parameters. And this is a downside to having the GAM attention module. Yeah, as you can see, there are like much more additional parameters we had to train compared to ECA. This could be a key factor due to which GAM didn't perform well on the lesser training we have done on it. And we have given the same number of epochs of training for all the models just to be sure that we are not compensating on one side. Uh, Moving on to ECA, ECA follows a very simple approach. They have a one-dimensional convolution which is done across the image. And this initially was just done as a means for training ourselves to and learning how to add attention modules into the YOLO, but it turned out that this ECA module performed much better than GAM, and this could possibly be due to the fact that it has much lesser training parameters compared to GAM. And due to this, we have added the ECA attention module as well. And here is the whole architecture with the GAM attention module. Although it's not that clearly visible, I think, on the big screen, I'll just explain. Right before the head layers in the back and the neck, we have added the GAM attention modules in 3 places. And each of them is right before the head. And similarly, we have done the same with ECA attention module as well. Now, what we have done in the hybrid module is that in the first head module, where the number of the image size is the least, we have added the GAM so that it can be trained the best. In the second part, we have left it without any attention module, as even the YOLO V11 itself was performing reasonably well. So this could have performed well by itself is our hypothesis based on which we left it as it is. And in the last one, we have added the easy attention module. Thanks to its lesser trainable parameters, we can have it compute on the larger size. And coming to the results, you note that the map scores are much lower in the base models, and that's also due to the fact that we have only trained them for 100 epochs, and this was just to make sure that to identify which is the best one we can choose out of the following. And then from those, we identified that you. Hmm? Actually, okay, I'll continue.
Yeah, please.
Okay. Fine. So we have ran the base models only for 100 epochs, and out of that, we found out that YOLO V11 is the best. And then following that, we have done the 150 epochs on the V11S with the attention modules, all of them. And based on that, we have found the YOLO V11S hybrid, which has the gamma and DCA to perform the best. And although we could have ran for more epochs based on these, we can say, but due to constraints with the time and resources, we couldn't do further. And you can see some images of how it classified on the left side, we have the actual image where it shows which all are the ships and all. And on the right side, we have the what the model predicted. As you can see, for EC, it was not able to do much. Like many of the images, it wasn't able to see any ship in it. But the aircrafts are reasonably well detected. And the gamma attention managed to identify the ships pretty well, and perhaps too well. It even identified a lot of false positive, it seems like. And when it comes to the GAM along with ECA, it averages out both sides. And
Nikhil, you have 1 minute left. You please conclude.
yes, sure. And yeah, to conclude, the YOLO V11S with the hybrid model with the EC and GAM module performed the best. And for future scope, we plan to have the benchmarking models being tested on this approach. Since in this one, we have only used the Sky Fusion dataset. And finally, we can use other attention modules, or we can try for many different approaches to the same problem with the attention modules. These are the references used in this PPT. Yeah, thank you.
Thank you, Nikhil, for your presentation. So I again go back to the audience for any question. Anyone from the audience? Anyone wants to ask any question? Okay, so since there is no question, so Nikhil, I have 1 or 2 questions for you. Can you hear me?
Yes.
Now, when you show your data set, I see that the class distribution that you showed, this slide. So 65% vehicles, 18% ships, and 17% aircraft. So do you think this data set is a balanced data set?
No, it's quite class imbalance, but this is on the number of instances within each image and not on the number of images itself. But the number of images
Face
we
any
have
problem
balanced out.
with this data set?
Can you repeat?
Oh, as far as the result is concerned, you don't, or you don't make any arrangements for making it balance.
Yeah, we didn't further look into balancing the number of instances because with this distribution itself, it was giving reasonably well results. But the initial distribution without the extra data augmentation we did for the ships, it wasn't performing as well.
You have done your experiment only on this data set only. Is there any other data set that you have tried?
No, we haven't. We are considering using the benchmark models, benchmark data sets like as shown in the future scope.
Thank you. Thank you very much. A big round
Thank
of
you.
applause for the speaker. So with this, I think we come to the end of this session. Thank you very much for your patience. I see that this next speaker is already with us, Shubhamay sir. So let's end this session and move to the next session. Thank you very much.
Thank you, Shujoy sir, for conducting such a dynamically changing session, just like as dynamic as you are. We would like to request Professor Anup Kumar Sen to please facilitate Professor Shujoy Saha. Thank you so much, sirs. Distinguished guests, delegates, ladies and gentlemen, we now move on to the final segment of our morning agenda. We are honored to host an invited talk on the topic Nonlinearity of Boolean Functions, Combinatorial Results with Cryptographic Significance. Our speakers is the very well-known and respected Professor Shubhamay Moitro from ISI Kolkata. To chair this prestigious session, I would like to introduce Professor Aniruddha Dasgupta. Professor Dasgupta is a technical business analyst, researcher, educationalist, and Australian energy regulator. He earned his BE degree from Jadavpur University, going on to pursue an MSc from University of Guelph and his PhD from University of Wollongong. He has more than 25 years of experience in the ICT industry and the academia, with full SDLC experience in managing the design, development, and deployment of applications in several industries. Over the years, he has assumed a wide variety of roles such as project manager, data scientist, business analyst, system architect, designer, and programmer, and has managed development teams across continents. He has a deep understanding of modern machine learning and their mathematical underpinning, and has worked in areas such as classification, recommendation systems, and natural language processing. He has also a huge experience in teaching and research at universities worldwide. Sir, I would please request you to come up on the stage. I hand over the stage to you to please welcome Professor Shubhamay Moitro.
Hello. Yes, it's a great pleasure for me to introduce to you Professor Shubhamay Moitro, who is quite a known face to all of you. So Professor Moitro is a senior faculty member at Indian Statistical Institute, Kolkata, and specializing in cryptography and quantum computing. With a PhD and MTech in computer science from ISI, he has contributed extensively to areas such as Boolean functions, cryptographic protocols, and post-quantum security. He has authored over 200 research papers and currently leads the R.C. Bose Center for Cryptology and Security as acting center head. So please welcome Professor Moitro.
Hello, am I audible? Yes. So thank you, sir, for kindly introducing me. And when I come to such conferences, I understand that I have done a lot of things. But sincerely speaking, we have done very little on certain topics in the domain of computer science. The only added thing is the experience. That is from 1988, we have started learning a little bit of electronics at Jadavpur University. Shubhashish was 1 year junior to me at that point. Later, we did MTech at ICAA Kolkata. So from 1988, we have some experience on basics of electronics and computer science. And as you might be knowing that Boolean functions are actually, Boolean functions means, you know, AND or NOT gate, truth table, and all those things. So this is actually the, in my understanding, this is the heart and brain of computer science. It starts from Boole. So the name Boolean comes from Boole. So a self-taught mathematician, philosopher, and logician. So initially the talk is actually very technical, the later part of it. So what I thought that it is impossible to convey the research depth and ideas. I'm not that capable, so that I can, we are working on these topics from mid-90s. So we really cannot explain everything in this short time. So it would be more a talk related to entertainment, not to technology. So this is our plan. If we can at all finish at 1, or we may a little bit of more time we can get. So basic definitions, nonlinearity and Walsh spectrum of Boolean functions, the case for even number of input variables. So like AND gate with 2 inputs, it is a Boolean function on even number of input variables. Now, if you consider a multiplexer where there are 2 inputs and 1 select and 1 output, then it is 3 input. That is on odd. On even and odd, there are a lot of issues. For even number of inputs, there are bent functions. Bent means which are away from nonlinearity. So when I saw my face there, it was on linearity of Boolean function, in missing or in silent. So, but that doesn't matter much. We can name this talk also as on linearity of Boolean function. So bent means which are in Bengali beka, so which are far away from straight things actually. Then we will discuss the case for odd n, bent concatenation bound. If you remember truth tables, if there is a truth table, if you concatenate it twice, then the truth table would be doubled, size of it would be doubled. So the variable, input variable number will be increased by 1. So if you start with even variable and concatenate the truth table one after another, then it would be a Boolean function on odd number of variables. So that is actually very interesting. That we call bent concatenation bound when we calculate nonlinearity. But if we can exceed that, if we can improve that, that is one of the most challenging problems since 1970s or even before that. And we are glad to work in that domain. We got some new results that are open for almost 30-40 years. But you know, academics, as we do not remember the name of Nobel laureates, similarly, these results will never give you fame. So you have to be in politics to have your name known. So our results are important. I'll try to explain that. And then several persons works in this area, Dylan, Patterson, Wiedemann, and then the concluding remarks. But before that, I would, so last night I added these slides. These were also prepared earlier. Which are actually non-technical points and how computer science comes into play, how Boolean functions are related to that. So they are society, politics, science, and technology. These things are very much related. We would try to talk about those things. Before lunch, generally people do not sleep. So I might have skipped them. But still, you might find it more interesting than technical things of Boolean functions. And then Boole, Turing, and Feynman. This is my definition of a triangle of computer science. In my understanding, these 3 people should be referred when we talk about anything related to serious computer science, or I would say fundamental or classical computer science. Classical does not mean we won't include quantum, because Feynman introduced that. A little bit on Boolean algebra, which was done by Boole, Turing. All of you might be knowing his name, and Feynman, who proposed the quantum simulation, and Boolean functions can be understood, or quantum computing can be understood in terms of Boolean functions also. So actually, we need to talk about two revolutions. One revolution is the industrial revolution, and another revolution is the computing revolution. So if you compare these two things, you would find that 1760 to 1820, 1840, that time, we had industrial revolution, and that had made a huge impact on society and politics. So the transitions included these things. You may know very well from class 7 or 8, we have studied those in our school. Shilpo Biplab, Industrial Revolution. And the most important outcome of that is capital, which talks about a society where people can generate capital. And again, politics related to that. And now the computing revolution, this is again what I defined on my own. There might be some papers on computing revolution in good journals. I'm not referring them. So computing revolution, I would say it's started when Boole identified those things, though the idea of computation was not there. The basic thing is you have 0 volt and 5 volt. 0 volt is ground, and 5 volt or 1.5 volt or 12 volt, that you can interpret as 1. And with zeros and ones, you can actually do most of the computation. And then 1930, so that time Alan Turing proposed more formal models of computing, and that part is limited to classical physics. Until the end of 19th century, we believe that Newtonian laws or Maxwell's equation, those will dominate the thing. But quantum computation from 60s gained some momentum. Actually, quantum physics got momentum from 1910 to 2030, that time. But getting the model of a simulator, that Feynman told in 1981, and most of the developments are in 21st century. So we are passing through an era of computing revolution. So, and now, since there are two revolutions, revolutions are not always the French Revolution or the revolution at Shingur or Nandigram, not those. Other than that, there are also technological revolutions. So, and those are generally not taught in history books in our schools. So, 2 centuries apart. So, one part of it is muscle versus brain and their limitation. So, the muscle thing is hard to force people to work. And not only hard to force, they cannot work continuously for a very long time. And you cannot, if you have 5 computers which are not working, you can take the parts from them and you can put them together. At least you get 1 or 2 computers which should be working. Unfortunately, medical science is not that improved yet. So you cannot take body parts until the person that work harder. And then again, there is the social revolutions we had made and the difference between industrial revolution and computing revolution is that the social and political scientists at that point of time were top grade intellectuals. If we look at the present international standard or stature, you won't find a lot of people who are doing philosophy and computing together. In England, there are some courses, mathematics and philosophy kind of thing. In our country, that is almost absent. The new education policy talked a little bit about that, whether we can connect those things. But what is absent nowadays is we do not have a person who works in the domain of social science or philosophy and understand computer science very well so that they can guide us. But at that time, just to compare things, if you talk about Karl Marx, that time these concept of derived functions, differentials, differential calculus, Taylor's theorem, Maclaurin's theorem, Lagrange's theory, those things were being developed during the time of Industrial Revolution. And Marx and Engels, who are actually talking about politics, they could understand all these things. That day mathematics, they could understand, and they wrote letters to each other. There is a famous mathematical manuscript of Karl Marx. So present time, we really do not find a social scientist or a philosopher who can read quantum computation or the hierarchy of classical computation. Subhashi should be telling P on superscript NP, what is the meaning of that? So these kind of things, nowadays there is a big gap. So that is why the computation, the way it is taking care of the world, that is only understood by the technologists, not by the people who are in social domain. Yeah, trying, but so giving, trying to give a few, and you kindly you have given the opportunity, taking this time. So this is Bull. I always talk about death because sometimes death is related to life, and how these great people died is very interesting. So Bull, his book Laws of Thought and all of these we talk very quickly. So this is the death. That is a man of such stature went without an umbrella, and he had cold, and at that time people believed that remedies should resemble their cause. So she wrapped him in wet blankets, and unfortunately he died. So 15 to 64, something like for 50, less than 50 years, he died. So he could have done a lot more. So his contributions are related to these things. So at that time, possibly he couldn't understand that things would move that fast in this century. But most of the things have been developed by him on which we work. And then Alan Turing. So one of the greatest intellectual of the previous century. And he had, I think we should have other opportunity to talk about life and work of Turing, imitation game, and what we talk about AI and ML nowadays, a lot of people getting Nobel Prizes. He is not very much referred, but the basic idea of imitation game that ChatGPT is doing now is basically his idea, 1950 paper, the imitation game. And his death was also unfortunate. In fact, more unfortunate. That time, the Western society couldn't understand. And now how he died, whether he was killed or he committed suicide, is not clearly known, but the story is related to apple and cyanide. And there is a famous movie called The Imitation Game. If you have not watched it, in YouTube, it is free. You may have a look. And these are his contributions. Von Neumann also had similar kind of model. In fact, I find von Neumann's model much simpler, where you have a processor and a memory, and you can communicate with some wires. But Turing's model is very powerful when you consider the tape and the head. So you learn that in automata course, DFA, NFA, then context-free grammar, push-down automata, and then we go to Turing machine. The basic idea is what any classical computer can do, it can also do those things. And he has a very strong contribution in the world of cryptology, in fact, practical cryptanalysis. So then this person, so he's another method, what we should say, theoretical physicist basically. So he has also contributed a lot in the domain of physics and computer science. In particular, in 1980s, he actually proposed a formal model of a quantum simulator. And this is his end. So these three people have directly contributed to the domain of Boolean function. And as you can see, any program that you are writing, you can look at it as a sequential logic kind of functions by using some flip-flops and some combinational gates. On the other hand, even you can replace the flip-flops also, the sequential circuit by combinational circuit, but then it would explode. So if you see some kind of adder also, so generally adders, we have some kind of delay, but if you have to go for a carry look ahead kind of adder, then you would find that the circuit is exploding. So these are the areas where Boolean function came into play. So lots of information related to Feynman, his contribution, and later quantum computing like AI/ML, they are also getting high importance in the domain of Nobel Prize, like Yunus or Macedo, that lady, they are getting Nobel Prize for Peace. Similarly, they are getting Nobel Prize for Sciences. So now we are coming back to the topics of Boolean function. We will So now the slide should look quite dense. Invariable Boolean function, I hope all of you have written sometimes truth table. Left hand side you write down the input variables and right hand side you have the outputs. So this is one implementation of Boolean function. And so there are n variable Boolean functions, while left hand side you have n bit patterns. So how many such patterns? 2 to the power n patterns. So this is a 4 variable Boolean function. You see 4 bit pattern, 2 to the power 4, 16 many patterns, and corresponding to each pattern you have an output. So 2 to the power 4 many outputs. So how many n variable Boolean functions are there? 2 to the power 2 to the power n. So this is one implementation, and another implementation is you can write it in algebraic normal form. This plus is actually XOR. So with XOR and AND x1, x2, with this you can implement any Boolean function. And the problem of solving one-to-one mapping between the truth table and the algebraic normal form is a very interesting exercise. And from algebraic normal form, you can put all the input values and get the truth table very easily. But on the other hand, if you are given the truth table, computing the algebraic normal form from that, writing that program is quite interesting. So, and weight of a Boolean function, by this we mean that at how many points the output is 1. So if we consider this Boolean function, the weight of this Boolean function is 8. Out of 16 places, there are 8 places which are 1. So these Boolean functions we call balanced. Why these are important? Because randomly if you choose an input, the output would be 0 with probability half, and the output would be 1 with probability half. So they have huge application in the domain of cryptography, where you want some kind of randomness. So a large truth table. So you have a truth table like this. This is 16-bit. Now consider left hand side you add another variable x5. So you will have 32 patterns, and then you can have this output in the first 16 places, and later you can put another 16 outputs. So you will have a 5 variable function from 4. So a large truth table can be seen as concatenation of small truth tables. And this can again be seen in algebraic normal form as 1 plus xn, plus means XOR, if one of the upper side function. So when xn is 0, 1 XOR xn will be 1. So f1 function will be activated like multiplexer. And when xn is 1, then f2 will be activated, because then 1 XOR 1 would be 0. This first part will vanish. So this is one interpretation. Then for complement, we have the notation f bar in algebraic normal form. If you have the algebraic normal form of f, just add or XOR 1 with that, you will get the complement. Functions of degree at most 1 are called affine functions. So you won't have any product term. Those are linear or affine functions. So this is the form of linear functions. These are very important. These are related to first order Reed-Muller code. And in 70s, when possibly there was some requirement of communication from outer space or Mars, somebody sent something. So that communication was encoded using Reed-Muller code. And the nonlinearity is, if you have the set of linear functions, they have their truth table. How far is your function from that truth table? So there is one circle in which you have all the linear functions. So how many linear functions are there? A0, A1 up to AN. So n plus 1 many binary patterns. So you can have 2 to the power n plus 1 linear functions, linear or their complement, that means affine. And if you write them all, and if you take any other pattern, and if you try to calculate the Hamming distance from this set, that is some functions should be closer, some further, but minimum value, then that value will give you the nonlinearity of the Boolean function. And in several applications from circuit complexity, which gives you greater insight to computation, and in cryptology, we are in requirement of such patterns, such binary patterns, which are far away from these linear functions. And at any day, you have 100 open problems in this domain. And out of them, we solved 4 or 5, which are good. And we now have at our hand 10, 12 problems on which we are working. The advantage between the advantage at our time compared to 70s or 80s is that the computation power is now huge. So there are a lot of problems now where other than mathematicians, if serious computer scientists who can actually write very good programs in software and actually they can design some good hardware, even by some clever search. In fact, we have done some clever searches in last 20-30 years, and the results could be obtained by a proper handshaking between mathematics means finite fields. I missed Galois in this talk. I would have loved to talk about him, but if we have good understanding about Galois field and primitive polynomials, Niederreiter has a very good book there. And we can write down C programs corresponding to that. Python won't work here because Python is much slower. So we have to write C programs, we have to use assembly language, we have to distribute the program in several machines. And a lot of results are still achievable by writing good programs also with the combinatorial understanding. Because if we like to see a finite field, we really cannot write 0, 1, alpha, alpha square like that. We have to take a primitive polynomial, x to the power 4 plus x plus 1 equal to 0. And then with that primitive polynomial, we have to map these elements of the finite fields to the bit patterns. And these kinds of programs are, I won't say non-trivial at this time, but these programs require some basic understanding of serious computer science. So this is the nonlinearity of Boolean function, and that can be understood in terms of Walsh spectrum. So this is something related to Fourier transform in real domain. So this is, some people call them Hadamard transformation, some people call them Walsh transformation, some people call them Walsh-Hadamard transformation. So these people have contributed. And what does it tell? It tells Walsh spectrum of a Boolean function at a point omega is at how many places that point, that Boolean function is matching with the corresponding point of a linear function, and how many points it is not matching. And so we go for adding them when it is matching, we are subtracting them when it is not matching. So what would be the furthest scenario? When this Walsh spectrum value is 0, because half of the places it will be matching, half of the places it won't be matching. You may ask that why I can have more places not matching. But if you have more places not matching, then corresponding to that linear function, you can have its complement, and then you will have more matching. So half is the upper bound. So this calculation, and this helps us something like, or not something like, exact algorithm like first Fourier transform, where and first Fourier transform, we must relate it with first Fourier or quantum Fourier transform major result by Shor, where we can show factorization is polynomial time in quantum domain. That is also related to Boolean function. So here, this is the Walsh spectrum and how you can calculate that quickly. That method is given. In the first line, you add first two locations, subtract first two locations, add first two locations, subtract first two locations. Then you jump by 1 with a gap of 2. Then you jump by 4 with a gap of 4, and you get the result. So the complexity is basically order n log n, if you consider capital N as 2 to the power small n. So in terms of input variables, it is small n into 2 to the power small n. And if you take capital N equal to 2 to the power small n, then it becomes n log n, which is naturally, you know, the complexity of Fourier transform. And there is a famous Parseval's theorem, which is related to power in Fourier transform. In communication or electronics, you may have seen that if you have a signal in time domain, you go to Fourier transform, and then you can calculate the power by taking squares of some coefficients. Similarly, if for any Boolean function, if you take the square of all the Walsh spectrum values, it is always 2 to the power 2n. Please remember that there are, how many omegas are there? 2 to the power n many omegas. So 2 to the power n many omegas, corresponding to that, you are getting the Walsh spectrum values. All the values you are squaring, adding them, you will always get 2 to the power 2n. So now, first Walsh transform, it requires order n into 2 to the power n time, that we told. Then nonlinearity is that formula. That is, calculate all the Walsh transform values, find out the maximum out of there, that maximum in terms of absolute value, and half of that you subtract from 2 to the power n minus 1. That will give you the maximum nonlinearity. So very simple calculation. I'm not going into that. You may do it by hand. And when you are getting half of max of that, then I'll come in the next slide. You have some bound where it can be, it is actually strictly less than 2 to the power n minus 1. It cannot reach 2 to the power n minus 1. And what are the related areas? Cryptography, where confusion in designing cryptographic primitives for symmetric ciphers. To resist linear attacks, you need highly nonlinear Boolean functions. And for coding theory, it is covering radius of first order reticular modal code, which is, for a long time, it has theoretical and practical importance. Now, let us get into the bounds. For the students, please do not prepare slides like this. People would be very unhappy. So I have tried to minimize the number of slides, because if you take a printout, then you spend less papers. So maximum nonlinearity is less than equal to 2 to the power n minus 1, as I have already told, because if you have some distance more than that, you take its complement linear function and it would become less than that. Then can we get a stricter bound? Yes, because Parseval's theorem tells that all the Wald spectrum values cannot be 0. Their square of sum is 2 to the power 2n. So nonlinearity is maximum when max of that value is minimum. This is achieved only when all the values are equal. So all the values are equal. So that means total 2 to the power n values, their square adding 2 to the power 2n. So all the values are equal. So one value square would be 2 to the power n. And then you take square root of that, because you earlier have square on that. So the value would be, when everything would be minimized, then it would be 2 to the power n by 2. So nonlinearity must be less than equal to 2 to the power n minus 1 minus 2 to the power n by 2 minus 1. So this nonlinearity at the right hand side, this is considered as the bent functions nonlinearity, which is the maximum nonlinearity you can achieve for any Boolean function. Now, the way you have used the nonlinearity definition by distance of two binary pattern, this cannot be irrational, right? But if you take n odd, then this definition is not correct, because then 2 to the power n by 2, 2 to the power 3.5 say, it would be an irrational number. And in that case, you cannot have integer values. So the maximum nonlinearity for n even is this thing, and the functions that achieve these values are called bent functions. And bent nonlinearity values for small n's, we have written some of them. So initial work by Dillon and Rothaus during mid-70s, later huge literature, Claude Carlet, C.M. Mesneger, and there are many contributors, Paula Sarkar from India. We have also done some work. So some kind of around 500 top level papers in good journals. And some problems are still very complicated. Like n equal to 8, we know all the bent functions. So it was done in 2010, but n equal to 10, we could not do after that. That exactly what is the count. So this is one problem which I believe is achievable and would be published anywhere, where it requires some kind of understanding of Boolean functions and some kind of search to find out the number of 10 variable Boolean functions where it is not completely characterized. And for n greater than equal to 10, it would be harder. 12, 14, 2 to the power, it is increasing. So, but this is the current status of Boolean bent functions. Now, how the bent functions can be constructed? The bent function, as I told you, that small functions, the truth table of them can be concatenated to get large functions. Very interestingly, if you concatenate all the n by 2 variable affine functions, one after another, that will give you a bent function. So you are taking 0 nonlinearity functions and concatenating them, you are getting maximum nonlinearity. Why does it happen? Because a linear function, though it is linear, it is furthest away from another linear function. So from that argument, you can actually see f1 is a function where 2 variable linear functions are concatenated, and it gives you a 4 variable bent function. And the second thing is direct sum. You take a Boolean function x1, x2, which is the bent function on 2 variable. You take another Boolean function on two variables x3, x4. When you XOR them, the variables are different. So you get a 4-variable function. If you write down, that would also give you a bend function. So the first one is famously known as Majorana-Macfarlane type Boolean functions. And the second thing is known as direct sum. And we will talk about Dillon's construction also, which is related to symmetry and little bit of finite field. But so far, you really do not need anything related to finite field, just basic things. So now the question is, what would happen for n odd? For n odd, you cannot handle like bend function because n is odd, 2 to the power n by 2 won't work. So in that case, you can get a nonlinearity. You can see there, we have put very simple thing. We have put a ceiling. Bend concatenation bound tells that if you take two bend functions, concatenate them one after another, they can be same also. Then you get an odd variable Boolean function, which gives you a nonlinearity 2 to the power n minus 1 minus 2 to the power n minus 1 by 2. So earlier it was n by 2, outside it was minus 1. Now we are getting the minus 1 is going, so n minus 1 by 2 for n odd, there is no problem. There, what you find that you can get lot of functions with very good nonlinearity. You get a bend function, you use that. The problem is it the maximum nonlinearity? Now, in 1972, Barleykamp and Welch in IEEE, most of these papers are published in IEEE Transactional Information Theory. So, Barleykamp and Welch, they have that time, even searching 2 to the power 5 was not easy. So again, they do some mathematics, some searching, and they characterized all the functions and told, see, for 5 variable, for 4 variable bend nonlinearity is 6. For 5 variable, you can get 2 into 6, 12. You cannot get more than that. Then, in 1983, you see the difference. 72 and 83, after 11 years, Michelwitt shown that 6 variable bend functions have nonlinearity 28, and you can only double that, 56. You cannot go more than that. So 80 he could find. For publishing, he took around 3 more years. And Michelwitt's paper, you really cannot read. Terrible paper, intra-published in IEEE IT. We also get such review comments, and then the papers are not published. We have to revise it. But somehow Michelwitt could manage it. It's a challenge to read that paper. Later people tried to simplify it. But he could show that for 7 variable, you really cannot break the bend concatenation bound. And then the main question is, can the bend concatenation bound be beaten? Almost at the similar time, Patterson and Wiedemann, they could show, yes, we can break that. And they could show that above bend concatenation, you can add plus 20. This is famously known as Patterson-Wiedemann construction. And now we have a very nice story here. So during 1998, 99, I was working with Professor Bimal Rai and Polar Sarkar. So we got the paper of 1983. Naturally, we are looking Michelwitt's paper 1983. Seijenthaler has a very good paper on correlation immunity 1984, that time, 1984, 1985. So their paper we took. We have taken, they have told the orbits and all those things related to finite field, tower of finite fields and all those things. Writing programs are very hard. I wrote those in C, and we were not getting this nonlinearity. So then naturally what we tell, as we tell our students, that students always come to us, our program is not compiling. So we tell that it's your problem, not the machines or mine. So similarly, that time we were not getting results. So people told, no, you wrote it wrongly. So then ultimately I wrote to some people in Europe that what is happening? I wrote this code, please see my code. And nobody would generally try to debug your code. So that time, Professor Anne Kantut, almost our age, she was working in India. She told that, no, their orbits they have told. I have not checked the orbits. There was a very simple search of 10-bit pattern. I could have searched and found the correct orbits. I didn't do that because in the paper the orbits are given. Simply out of 10 bits, they clearly told that these 5 bits should be 1. And those 5 bits I am making 1. And then it will please see the paper of 1990. And then I found the 2 orbits they have given, the 5-bit, 2 5-bit patterns they have given in 1983 are wrong. And it can never happen. Then I tried to understand what happened actually. So then after some communication, I understood that Patterson and Wiedemann, they were working in NSA. So they possibly intentionally given two wrong bit patterns. Anybody writing a program could have found that. Nobody wrote. Naturally, these are not very interesting for research. So ultimately, we got the 1990 paper, which is half-page correction in IEEE, and we could get those functions. And the next question is, can we improve these 20? The chance is very low. We have worked. Several works are done. You cannot improve it more than that. So this is the story of this paper. Then what was open? So you can see that 15 onwards, with this 15 variable function, you can go for 15, 17, 19 that way. You can use those functions. So problem is solved for 15 to upper side of odd numbers. And the problem is solved for 7 downwards. So 3 more odd integers are staying, 9, 11, and 13. So we started working, and I was invited in Turkey in a national workshop. I went and I met some Turkish people. They were also coming to India before that in Indocrypt. And they told, okay, let's try some kind of search. So once I come back, Selçuk told me that he got a function with nonlinearity 241. So 9 variable function is 2 to the power 2 to the power 9, which is 2 to the power 512. You really cannot search, but by some simple understanding, we could reduce that to 2 to the power 60. Even at that time, 2 to the power 60 search is not possible, but we tried some search and we got, yes, we can find out a function where the 8 variable Boolean function, bent function, has nonlinearity 120. You can double it, you can get 240, and you can break this bound. We got a 241. Later, Selçuk tried a little more thing and they got 242. So here there is still a chance of 243 and 244. Our idea tells that if we can work hard, there might be some functions of 243 and 244. And if you look at that bound, 2 to the power n minus 1 is actually 2 to the power 9 minus 1, so 256. And 2 to the power n by 2 minus 1, so 2 to the power 4.5 minus 1, so it is 2 to the power 3.5. If you calculate, 2 to the power 3 is 8, and 2 to the power 0.5 is 1.414. So 8 into 14. So that would give you something like 12 kind of thing. So that way 244 is the exact bound. So this is an open problem, that if somebody can find out a 244 or prove that it is not possible, both are very important results. So second open question I leave for you, which would immediately produce a paper. That is, if we can do something for 9 variable Boolean function and cross the bound of 242. 9 variable Boolean function, if you put the values there, n equal to 9, you will get 244. So we could get 241 and 242. Not we could get 241. I should not tell we also, because they found the function. They allowed me to be a co-author because I have given them the idea of the algorithm. And then they also got 242 by more search. But 243 and 244 are still open. So this is the question. And the next question is that for 21, that their bound translated to 21 is 160. We have got some actual search in that space that we can solve in 2016. We got 61, which is much less than 160. But then we have a paper in Siam Journal of Discrete Math where we could show you can beat 160. So that work we are still doing. I'm not getting anything yet. So that is another work we are continuing. We need very strong programmers and very strong machines for that. Now we are again, so even, odd, and now we are coming back to n even again. N even, when we are now concentrating on n even but balanced function. Bent functions cannot be balanced. Bent function in the output, there cannot be equal number of ones and zeros. But balanced functions are important for cryptographic things. So balanced functions, when you calculate from if you want to make it balanced, nonlinearity would decrease because you cannot increase the bend nonlinearity. It is proved. You cannot have the bend nonlinearity because you cannot get balanced. So nonlinearity will decrease. Nonlinearity cannot decrease by 1 because everything is in even. So nonlinearity would decrease by 2. And now we could prove, or not we, many people have proven that for 2 variable, 4 variable and 6 variable, you can get a nonlinearity which is 2 less than the bend nonlinearity. So up to 4 and 6, this problem is solved. Now the problem comes from 8. 8, what is happening? For 8, the bend nonlinearity is 120. And simply by using some construction, I'm not getting into that, getting nonlinearity 116 is possible. So 120 is your bend function nonlinearity, 116 is what you can get easily. Not easily, I should not say easily, but with some understanding. And now can we obtain a balanced function having nonlinearity 118? So this problem was proposed by Dobertin in 1994. He died early 2000 that time. He was a very good researcher in this domain. So he posed this in 1994. And we are trying very hard on this problem. At least this problem is in our every night's dream, because we believe the nonlinearity 118 balance function is there. And in Crypto 2000, we got the last theoretical result that if you consider 8 variable function and it is a concatenation of 2 7 variable functions, and then all those 2 7 variable functions must have nonlinearity 55 and algebraic degree 7. But searching all 7 variable functions with nonlinearity 55 is still impossible. So in general, this is the conjecture that for n even, can we construct n variable balanced function having nonlinearity greater than 2 to the power n minus 1 minus 2 to the power n by 2 plus nonlinearity of balanced function on n by 2 variables. So by modifying bend functions in several ways, we couldn't do. Still we are working, and let's see. So this is another problem where we can collaborate. And these problems are known in the open. You can try on your own also. Nonlinearity question for n odd. In odd also, the Patterson-Wiedemann functions are not balanced. So we tried for balanced functions what we can do. In Crypto 1993, so correct paper by Patterson-Wiedemann is 1983. In 1993, Severi, Zhang and Zheng, they have done a lot of work. Jennifer Severi is also a very popular person in India. She is very old now in Australia, University of Wollongong. She usually used to come to Kolkata very often. So she could use the 15 variable function as a black box and did some mathematics and shown for n greater than or equal to 29, balanced functions exceeding bend concatenation nonlinearity is possible. But later, we looked into those functions. I told you that that time we were trying, and we could got many more results in this domain, and we could publish. So I think already 10 minutes over than the scheduled time. So very quickly to tell that there are a lot of smaller classes of Boolean functions. So if you look at the smaller classes, you get very high nonlinearity, and sometimes you don't get very high nonlinearity. So symmetric functions, Dillon's construction in finite fields, they give you a small or smaller subset that you may not search the whole space. It might be even impossible, but it is much smaller than 2 to the power 2 to the power n. So those classes, in case of searches, these ideas reduce the search space significantly, and that is exploited. And we are getting results, publishing some. Telling these would actually be very hard because Frobenius automorphism and all those things, tower of finite fields, these things I also do not understand very well, because then Subhashish might ask questions and I might get into trouble. So these are certain things where we have to sit together and explain, but the basic idea is you need to know group, subgroup, actually finite fields. If you use the plus operation and dot operation. If you forget the plus operation, if you the zero identity, if you remove, then you actually get a finite group. And on that, there are a lot of things where you can write down the programs, bring the finite fields to actually truth table domain, and do certain kinds of operations. And through that, we are still trying to similar to Dillon's construction. So basic idea is, I should say that you have a group, and in that group, you have a subgroup. So corresponding to that subgroup, there will be some cosets. And they are taking the subgroup and all its coset, you can have the full finite field covered. So in those subgroups, in each subgroup and its cosets, instead of putting different values, inside that you fix the values. So consider a group of, say, a finite field on 2 to the power 8 elements. So if you call GF 2 to the power 8 star, then you have 255 elements. Now, 255 would be divisible by, say, 5. So 5 to 55 means something like 51. 51 is 3 into 17. So 3 into 5 into 17. These will construct some other smaller subgroups. And once you locate a proper subgroup, then you decide in how many places you will give 0 and how many places you will give 1. So you take the subgroup, say corresponding to all that elements of the subgroup, you put the value 0. You take one coset, corresponding to that coset, you put all the values 1. Go to another coset, corresponding to that, you are putting all the values 0. So this way, if you do certain kinds of symmetry, that can give you very good nonlinearity. And at the same time, now the machine learning, top machine learning conferences, they also take a few papers which are on learning. Learning means Boolean function learning. It is not the machine learning. This is an earlier area. This is also related to machine learning actually. So they are also, people are publishing papers with these kinds of our ideas. In ISI, one group by Orijit Ghosh, Monmotho Roy, Saurabh Chakraborty, they are working. They are also getting very good results, competitive results in international scenario using these kinds of ideas. Yes, they're still not sure. Possibly one might come. No. Yes. Increasing the nonlinearity means you are far apart from the linear functions. And if you take a function which can be approximated well by a linear function, then you can go for linear attack. Linear cryptanalysis, which is a famous area. Matsui has proposed that in early 90s, 92, 93, which is known as linear cryptanalysis. And there is also binary affine approximation attack by Kunsheng Ding. So that is why you need nonlinearity. And you need, when you need something, then you always ask for more. No, but for n we have bounds, so yes, then the circuit size would be larger. So that is those things are there. No, these are very, believe me, these any 10+2 student, because we have never used any technique which is more than 10+2. Only for finite fields we need first, second year mathematics. Group theory, finite fields, vector spaces are generally taught in discrete math or abstract algebra or linear algebra in first or second year. We generally do not learn this. That is our problem. So, but understanding these things help a lot. So these are the subset calculations. So these are idempotents, and I'm not getting into these. And so I think this is the last slide. So now we are very strongly working on 21 variables. Why this is very important? I told you for 15 variables, it is 20 more than Venn concatenation bound. So that can be easily translated to 160 more than Venn concatenation bound for 21 variables. So 15 variable, we have a paper, the same paper, where 15 variable we are more or less sure we could not prove, but in a very large class we could prove that more than 20 is not possible. In 21 variable we got something more than 61 in a different method. See, we got a result which is suboptimal in a different method, but that got published because we could use the basic idea of Patterson-Wiedemann, not the idea of Bain concatenation. And then in CM Journal of Discrete Math paper, we could show that this 61 can be 196, which is more than 160. So if we can get that function, then we can tell that we could get the best functions after 21. So we could break the bound, not starting from 15, but 21 onwards. So here actually we have an integer programming problem. We have a 112 and 112 matrix, and we need some 112 bit pattern, which should run through that matrix, and the values corresponding to those equations should be in certain range, something like 57 to 72. So this we are working still for last almost 15 to 20 years. So we got 61 and nothing more than that. So thank you very much.
Thank you, Professor Maitra, for your insights. Now I open it to the floor to ask any questions.
Yes, please. Yeah. Please. Night iterator, yes. Finite fields and something. He has two books. One is very thick and another is smaller. No, but Night iterator's book is on finite fields. On the I have to check because nowadays many books are adding new authors and having the books published. So on finite fields. Yes, please.
And you mentioned some computation for some bounds, right? For the balanced functions and so. And I'm interested, what kind of techniques did you use? And you said you didn't succeed to compute. Do you think it's achievable with today's technology?
Yes, yes. I sincerely believe that for 8 variable, getting 8 variable, what is the problem? The bent function is of nonlinearity 120 and 116 is easily achievable. We cannot have an exhaustive search to check whether 118 is possible or not. But we can have some big search kind of thing, like the way we say, when we ask a question to ChatGPT, it answers, right? And sometimes it is very slow. So it is doing a lot of computation. So the kind of computation they are doing with lot of power and something, putting the machines in Siberia or something. So that kind of effort is not being done because here the outcome has not that importance. This is only some kind of theoretical question, but the theoretical question, mathematically, possibly it cannot be solved. Possibly, my feeling. Okay. So, but we are not even putting the effort. Putting the effort means not only that I need very good machines. I do not have time also to write down the codes. We are getting old. We have administrative works. So the problem we are having in these kinds of research, the results are absolutely tempting, and you can see the results when you are even at toilet. But the point is, we do not have a team. Only in Europe, some teams are working. In US, there is no funding. Turkey, there are a few people. India, we are a few people. People are not interested.
See, can I have another question, like short? But is there any connection with nonlinearity and, let's say, Kolmogorov complexity or randomness? Or
yes, absolutely.
Yes.
Kolmogorov has done those things, and what is that called? Another measure. I just forgot the name. The Terence Tao did some work on these things. So these are all related to randomness. They are proper definitions where you write probability below something and in bracket some algorithm outputting something. So these are actually there is a famous result by one Bengali on he got some very big award on resilient functions. I'm very sorry not to remember the name. Yes, Bengali guy. He got a Godel award very recently. Yes, I know him very well. I'm very sorry, getting old, forgetting names. He's very famous. He has written a very famous paper in Stokes or Fox, which is related to resilient functions. And those techniques are, we are not competent in those techniques, but they are using them. They're not doing any kind of search. They are doing analysis, but there is some gap between their techniques and our techniques. Their techniques are mostly asymptotic kind of, proving some complexity and bound, and our techniques are finding exact things. So now we are using some of our techniques in their domain, but their techniques, writing programs for those, the constants sometimes are becoming so high, they have certain results on nonlinearity. Goldrick has some result. Ishan, yeah, yes. And Goldrick has a lot of work. Goldrick-Levin algorithm is there, but those algorithms are more complexity theoretic. And when we are writing programs, the constants are sometimes 1,000, 2,000. So there is some gap. So, and understanding their work is also very hard because they are working 20, 30 years in complexity theory, where understanding those results. So I think we would get some more results. We are trying to learn.
There might be a bridge, right?
Yes.
Thank you.
Thank you very much. Yeah.
Any other questions?
No. There is a. I should take this opportunity. Even I'm late. There are two ideas now, two conflicting things that are running very seriously. Two conflicting things. So I'm in one side. I'm in one side means I'm Trinamool does not mean that BJP is no good. Okay. So the point is, there is a famous picture that comes in the talks of Vinod Boykunthan, that there is a human being and there is a dog. The human being, the dog is chained and the human being in his hand is the chain. And in one picture, the human being is told about something like theoretical computer science cryptography and the dog is machine learning. And other way around, the human being is machine learning and the dog is cryptology and theoretical computer science. So you understand in which group I am. So this is a very serious question, that who will control. So like Subhashish has correctly pointed out, that when we cannot publish a paper in Stoke, Fox or Soda, then we are going into New Rips or ICML or those top conferences. Those are also very competitive. No. Okay, I'm telling. Okay. So the other way around. Okay, I'm telling. So the point is, there is a big competition in these two domains. Both the domain have outstanding people, but as you see in two opposing political parties, there are outstanding people, but they can never come together. Academics is also like that. Finally, there is social and philosophical issues. So I think if these two communities can come together, work together, write down programs. People are thinking that telling ChatGPT, I'm working with ChatGPT now on the 21 variable problem, understanding those things, whether it can provide. Because Terence Tao had a very good proof he could get, he has told in his blog, through ChatGPT. So these kinds of things we have to exploit, they have to exploit us also. So that is not properly being done at this point. We are still at some distance. So if that gap is minimized, we would have many more outstanding results.
Suggest very easy or elementary, just some study material which can be suggested to second year students.
Modern algebra by Harstein. And again, Subhashish would have many comments on that.
The finite fields material in that book is
no, not good.
I'm asking for not for algebra, but I'm saying for finite fields. Niderator, they would be able to read and understand.
No. The point is whether they're interested.
No, suppose 5 students are interested and they are quite brilliant. So will they be able?
Surely, Niderator's book is.
Niderator book is okay. All right, fine. Thank you.
So I think.
Thank you, Professor Maitra, for your insightful talks. And thanks very much for the audience for listening to his talk. And hopefully more researchers would be interested in this field. Thank you. Thanks all.
Thanks a lot for kindly listening.
Thank you, sir, so much. That was really insightful and enriching. I would request Professor Dashgupta to please felicitate our speaker, Professor Shubhama Moitra. All right, now we'll have a small felicitation of Professor Aniruddha Dasgupta by Professor Dinobandhu Bhandari.
So this is not abelian. Let us have the workshops in smaller rooms.
Okay, so that almost brings us to the end of the morning session. We've had technical talks and that almost led us into social and philosophical thoughts. So I request the audience if you could please provide your valuable feedbacks for the morning session. And after providing the feedback, please, we could all proceed for lunch and be